Hello, my name is Olga and the topic of the report experimental and theoretical studies of the survivability parameters of a reinforced concrete spatial frame under a complex stress state. In accordance with the requirements of Federal Law 384 and the provisions of the Code of Rules 385, buildings and structures should be calculated for stability against progressive collapse due to initial destruction, leading to a change in the structural system. To do this, it is necessary to perform a calculation based on a special limit state associated with the sudden removal of one of the load-bearing elements. The calculation should be performed using a static, quasi-static, or dynamic method using spatial design schemes. If the first two calculations do not cause any special problems for designers, then the calculation in a dynamic formulation is more complex. At the same time, the requirements of the joint venture and the explanations of the methodological recommendations for the joint venture are quite general in nature and, at the same time, require highly qualified calculation performers. At the same time, a number of recommendations regarding taking into account or the possibility of not taking into account the compliance of the base, the desirability of additional inclusion of non-load-bearing elements in the scheme, the assignment of damping parameters, the assignment of the time of the initiating effect in calculating the time, and some others, directly affect the calculation results and must be specified. The purpose of the research is to study the features of deformation, cracking, and destruction of elements of a structural system with their complex resistance in extreme states caused by the sudden switching off of a vertical load-bearing element, stand. In the testing laboratory of Southwestern State University, a prototype fragment of a spatial reinforced concrete frame operating under complex stress conditions was developed and tested. The spatial frame is formed by two crosswise flat frames A and B with spans of 240 and 180 centimeters, respectively, intersecting along the vertical axis of symmetry. The crossbars of the smaller span of a solid section are made of B35 concrete, size 14 at 6 centimeters. The crossbars of the larger span of a composite section are made of B25 and B35 concrete with the same size. The reinforcement is made of spatial frames from Class A240 reinforcement with a diameter of 6 millimeters. At the intersection of the crossbars, a specially designed vertical support stand is installed, equipped with an electronic dynamometer to control the ground reaction. During testing, the rack structure can be slowly or suddenly withdrawn, removed, at a given point in time. During the loading process, angular and linear displacements, deformations, crack formation, and their opening width were monitored and recorded using a microscope and a digital camera. The diagram of the test setup, the placement of mechanical, electromechanical devices, and strain gauges are shown in Figure 1. To record fast processes, some of the strain gauges installed on the reinforcing bars were connected to a ZET017 multi-channel spectrum analyzer. The amplitude value of the vertical movement of the central point of the frame during the sudden removal of the support was additionally recorded with a mechanical caliper. A diagram of the formation and development of cracks is presented on the slide. Green indicates cracks formed during loading, red indicates cracks formed after the support is turned off. The first cracks were recorded at a load of about 900. A crack along the shear seam appeared at stage 6 at a load of more than 1,100 kilograms, on the lower surface of the crossbar at a load of 1,300 kilograms at stage 7. Until the moment of shutdown at stage 12, no new cracks had formed. Changes in existing ones were recorded. The opening width of all cracks was no more than 0.2 mm. After the support was turned off, the structure received damage, but a complete collapse did not occur. As a result of the experimental studies, new data were obtained on the stress-strain state before and after the restructuring of the system, the time of dynamic action from the removal of the connection to the achievement of the amplitude value of forces and displacements, deformations and characteristic sections, periods of oscillations and parameters of their attenuation for various loading schemes were determined. The choice of design solution for the frame and its testing scheme were confirmed by static calculations at different stages of the structure's operation. The static calculation was performed in a nonlinear formulation with the specified parameters. In accordance with the moment curvature graph, the moment of crack formation was noted, the load-bearing capacity was determined, and the range of loads under which sudden removal of the support was carried out was selected. The formation of cracks and control of the state of the section was carried out using standard procedures of the LyraCAD program. In general, The calculation model quite adequately assesses the stress-strain state of the structure, which is clearly visible in the cross-sectional graphs. The dynamic calculation of the structural system under consideration was performed in the mode of direct integration of the equations of motion according to the method given in the manual. The calculation scheme took into account the recommendation to take into account the compliance of the base and included non-load-bearing structures. Since the previous stages, when varying the consideration/non-accounting of the load device structures and the compliance of the base, it was found that in the specified section, the failure to take into account the compliance influenced the reduction in the magnitude of displacements by 30%. At the final stage, when the full load is reached, the support is turned off. Figure A shows the instrument readings at the moment the support was removed. In Figure B, relative deformations are conventionally shown from the beginning of the moment the support is turned off. In Figure B, an example of a change in bending moment over time, where the segment from 0 to 4s is the result of the application of the operating load, 4 to 6s is the shutdown, subsequent oscillation of the system. Let's compare the results of the experiment with the calculation. An increase in load and a decrease in the rigidity of frame elements due to the formation of cracks led to an increase in the time from the moment the support was turned off until the amplitude value of the determined parameter was reached, line 5 to 6. The period and the experimental attenuation parameter increased significantly higher than that recommended for performing calculations. Brevity, the findings are presented on a slide and are not read out. Thank you for your attention.